Good afternoon, everyone. Today, we'll be talking about how do we do a data analysis across disparate data sources. So myself, Raghunandan and Nitin Kashyap, we work at Huawei Technologies India from the Bangalore Center. We do work on big data technologies. Ranging from HBase and many other all the things which come under the Hadoop umbrella. But for the past 2 years, we are working on OpenLooKeng with a vision to make it a de facto engine in the big data space. We also have a vision to see that we can make it a solution which can be much simpler to use and adopt that. So of this today's slide, stands and what the status of that big data platforms and what is the analyst view on this, and where we think the OpenLooKeng solution would fit in and how it tries to solve the problems. And let's try to look at some of the business cases which using OpenLooKeng can be solved much easier. And we'll let's have a quick intro on of the OpenLooKeng. So if you look at the current big data market, as per the sum of the analysts from Market Research Future or IDC, it is around $53 billion US dollars. But this market is too fragmented and it been occupied by many softwares. If you look at this, there are so many systems per category. These are all in the big data scape and most of them are open source file. There are too many softwares which are there and we adopt for various use cases or maybe various business scenarios which are being got accounted. But we look at the same at the same time. Let's look at the big data software market share, the providers who are give. The biggest is by Splunk. Splunk is growing rapidly and still he just and the other big players who we call from the traditional databases like that, they control only up to 10%. And 50% of the market share is with other small players who are coming up or who are having a very different kind of solutions for that. But yeah, and also if you look at what is the data we are having, means the amount of we can see that IT services take up a huge amount of money. This all in US billion dollars, around $22.9 billion goes in IT services support and those kind of things. Hardware is much lesser and software also comes into the same range. So we feel maybe this major obstacle in all these things is the high service share, wherein that too many softwares, too many providers try. Look at the Gartner or Forrester. I have covered only two analysts, not gone into the other ones, Sulian or others. So if you look at the Gartner says that for a big data analytics, currently we are at somewhere the diagnostic. Why the problem happened? We try to analyze that. But what the businesses require or what the business leaders require. Wherein you, based on the data, you come to know beforehand that, oh, you need to take this kind of actions to have this kind of a result output. So these are all the prescriptive analytics, what we talk about that. And as in we move from top to the bottom, the human-centeredness decreases and it should become more machine-centered, meaning to say, we should have more solution based on us or give us suggestions what needs to be done like that. So to summarize what we have written here, the existing systems, whatever we are having, cannot handle the diversity of growing data sources. So maybe you will be having numerous data sources, maybe thousands of data sources with different formats, which we are finding it difficult to handle with the existing current data sources. And also the increasing out of that. How do we understand the proper schema in that? Also, the demand is for the real-time processing. Meaning to say, as the data has come at T+0, you want to process maybe for your fraud alert systems, or maybe when you bring the fintech, you want to release loans or you want to give credits at as soon as possible, not hold it on for days. Or when you're having a or maybe it's your power grid. So how do you handle that in the real time? So this needs a real-time processing, and we need to take care of the processing of the data at t+0. But with data complexity and with the data complexity and the data variedness arriving, the current platforms are finding it very difficult to handle this part. And also about the hybrid and the multi-cloud architectures. How do you have cross-cloud collaboration? Other ones. And this is happening that the data remains siloed and you are not able to bring all the data to a common platform to analyze that. If you look at what the Forrester started to suggest, it started suggesting something like a data fabric, wherein it involves all the data management capabilities. You need to have a catalog or data metadata management. You have a landing data which can be processed, which can be handled, and a very big and you have a very good ETL tools to handle this, so that all the things can come in together. I mean, just say Forrester is trying to suggest us that you need to have a platform which can work on multiple clouds or maybe on your multiple on premises and are able to give a unified view of the entire data. So that kind of a system is very much required in the current scenario. Also, if you look at the reference architect, the many companies, it almost looks similar. You have a data from various input sources. There are input sources can be many more. We have just put it few for simplicity. You have a landing zone where the data comes. You have an ETL tools, or you may adopt an ELT mechanism also, wherein the data gets enriched, the data gets cleaned, and you may run many ML models to and then you try to load them onto multiple governed data source. This governed data source is what I talked about in the first slide. So maybe it is an enterprise data warehouse, or it's a graph DB, or maybe a time series DB, or a columnar store, or NoSQL, many things based on the use cases. What are there? We may use too many different storage solutions to do that. So way of achieving this is something like your data virtualization, wherein which can give you a unified view of all this data. Also, the other advantage of this data virtualization is you can mask the data based on the access levels. Maybe who can view only few part of the data, it can be shared to them in a different way, like that. And then you have both batch processing or stream processing that we can take care of that. Virtualization as a very key player in achieving the data fabric solution. So he says that data virtualization can access many data sources, bring the data across all, give a unified view, give a unified layer or platform to execute the data, bring in correlation analysis, and the data what is analyzed is much. So we have many kinds of queries from the analytics point of view, and maybe we have different layers or different languages what we use to connect to different data sources, maybe different for OLTP, for OLAPs, or to connect to Hadoop systems or to NoSQL systems, which in turn are there on multiple data sources. Maybe the syntax is different and you're having multi-regions. So or to applications also, how do we query this data from anyone? Or for that matter, how the end user need to use different languages. This brings us a lot of problems in management and also in problems in efficiency in handling the data. So a simple solution would be something like a data virtualization engine, which can connect to all the different kind of disparate data sources. Queries, let it be your batch or your stream queries or interactive kind of queries, can fetch the data seamlessly and see that as though the data is all stored on a single data source. So with this idea or with this proposals, I also want to say what OpenLooKeng is trying to do here. OpenLooKeng is trying to give a platform which is something like you have a very unified data access to the northbound. Pretty good standard for all use cases. So below you can have a data source connection framework which can connect to multiple data sources. Let it be a OLTP kind of a solution, or an OLAP solution, or a NoSQL solution, or different engines. Have an connection framework which can connect to all these data sources seamlessly and give a to be built into the engine to take care of how to index the data across all so that the data fetching is much quicker, have a scheduling optimization to take care of efficient scheduling, many other functionalities to see that the data is fetched in as soon as possible so that the interactive queries or what we are talking about are served in seconds, maybe 1 second. So yeah, when you talk about this, we need to have a cross correlation, how to correlate data which are present in multiple sources. Maybe from the inputs, the data has been curated and stored onto different data sources based on the domain use case, but how do we bring all of them together for analytics? So we propose that OpenLooKeng sitting in this layer, having this kind of capability, will be able to bring an efficient data convert big data. So I just want to put it here, how the OpenLooKeng sits within the big data landscape for the fusion analytics. If you look at this, is the typical architecture what we follow in our big data platforms. You have so many engines for different various scenarios for graph or search or batch or stream. So you have the data management, which has the comes are stored in the data storages. It can be based on a text or an ORC, maybe a Parquet format or carbon data or any other format, a plain file or something like that. But yeah, these things get processed on multiple sources, maybe based on your ARM servers or your x86, typical x86 ones, or maybe on the cloud or on hypervisors, something like your VMs, what you want to run that. Yeah, handle all these things, maybe making OpenLooKeng the entrance to the data lake of this complete storage, and all can be accessed in a uniform way, simplifies the work of the analysts to focus more on giving meaningful outputs than trying to focus on how to build the solution, how to ensure the data of the solution. So when I want to bring that, what are the a typical big data analyst or would find in that one? So first one would be something for you, the cross source convergence. Why do we say it's a cross source? Like we talked in the previous slides, maybe you're having many data sources coming from for varied sources and stored in various engines or various data sources and using various engines to handle this. Maybe you're using Hive for doing some analytics queries where you want to have a very high throughput, your transactions per second are very high, or for a text search, you use an elastic search kind of a solution. But all of them have their own data sources. And to bring a data out of all these three, you need to have your own correlation engine, or you need to have your own platform, which has to have multiple languages to fetch from this and aggregate the data and give it to the above layer. Multiple pipelines you want to execute based on this. So a simple solution would be something like a virtualization engine like OpenLooKeng, which can connect seamlessly to multiple data sources, maybe it will be ES or HBase or Hive, and able to give the data in a uniform manner based on SQL 2003 or a uniform JDBC access for that. Now everything is going digital, starting from the governments to the businesses to everyone goes digital, and definitely all the data cannot be hosted on a single DC. You need to fragment your DC because of the size of the data, or maybe because of the locality of data, or where you want to process the data close to that. So when we want to do that, we want to process the data which is present in multiple you will need a switching platform to connect from one DC to the another DC, and then fetch the data from here. After that, fetch it from here, try to store it locally, and then do an aggregation. This is never going to be your real time or T+0 latency kind of manner to work with. So a best or better solution would be if sitting from one DC, without having a bridging platform in between, wherein seamlessly this DC also can be able to access the data from another DCs and able to do this. This helps for you to bring up the data seamlessly to access across data centers in a way that data is visible for all. Yes, also this helps you to control the security aspects, who can view what kind of data and to what level of abstraction data will have to be given. Also another thing is fetch the data can push down your computing to this data so that the analyzed data, which would be much smaller than the raw data, is transferred back. Also means helping you to avoid the bandwidth, network bandwidth, so that there is no network clogging on this. And the third case, what we want to talk about is how the one data saves the storage cost, meaning to say the data comes from multiple storages. Format, store the data in their own way. Meaning to say the data is stored in multiple forms. Maybe it's the same data stored in multiple forms, or the data which are completely different. So, and this data, we try to do an ETL to a data warehouse. This is something like your purpose database. For some specific purpose, you are trying to build this database, and you bring the data from here. So that means we'll be having multiple copies of this. Of doing this you need to like this. When you bring Elasticsearch, you have to use Elasticsearch for your text kind of a random queries, and Hive is good for aggregation queries for you. So because these engines are good at one particular thing, we need to bring the data and process using these engines for the same purpose. If we are able to build a solution which can so this brings a multiple advantages. There's only one copy of data for us to handle, and there is no latency in transforming data from one source to the other source, and data can be tried to fetch at your T+0 latency itself. The last one, what comes is we want to have a rock solid database experience. When we say about the database, what do we think that? Oh, about the stability, you have a uniform access to do that, and as number of queries I have fired, still the queries are answered successfully. There is no problem in the SQL queries, and also there is no lag. I'm always guaranteed my time, so that if 100 people query also, the output that comes is in the same time when 50 people also can query the same like that. So you may need to have to build multiple systems for that. You may have to bring a per query resource limit. How do you control the memory or the resources in per node? If one of the node goes down, how do you manage? How do you can transfer that task onto another node so that the data execution is success and the data can be returned back? And also maybe if one of the node goes down, when we use an OpenLooKeng solution, then the application layers need not be aware of the which node has gone down like that, because seamlessly we can transfer the data onto a different data source or onto query the data from a different worker and try to handle that data. So this is what I wanted to give the background of what OpenLooKeng is about and what is the motivation to bring up a data virtualization solution. Now my colleague Nitin will take us forward with the architecture and what OpenLooKeng is about. Nitin?
Yeah, thank you, Raghu. I think that was an interesting view on the whole business scape and the key features of our OpenLooKeng. So yeah, I'll take you to the under the hood of our OpenLooKeng. So as you see above, like in front of you is a typical cluster of OpenLooKeng. This is a typical MPP kind of a structure. You see a massively parallel processing engine, where we have a coordinator. Coordinator controls all the workers, which are really the workhorse of the system, which process all the data, churn all the numbers, and give you the results. Coordinator consists of a discovery service, which keeps track of the whole cluster and sanity and other things. Our coordinator is further created with a redundancy, providing HA. Active mechanism. They share the state across using distributed cache of the state. We call it as our state store. It's based on a Hazelcast cluster. Then all the jobs which are received by the coordinator, that's in form of a query, it further churns it down and breaks it into fragments and then pass it down to workers. Workers can access the data across various data sources. I think Raghu just now explained it very, very nicely. We have a framework called as the data source connector. Now, this data source connector gives out SPIs, which you can program your own data sources also. Our data source, which we package within OpenLooKeng, is quite rich. If something is not there, it can be easily implemented. Furthermore, the same cluster itself we provide as a data source. So that becomes our cross DC connector. So with this, what we get is you can really have a very, very large hierarchical clusters across your whole country or whole geography. Just to hit on the key features which we have discussed so far, I'll cover in coming slides. What we see is a really reliable framework which lets you run multiple queries at the same time. If one of the workers fail, the query, only that part of the query can be resumed further. We have a vector-based processing for all the data which we read from the various data sources, really scaling the performance up. I think we'll look at further deep in the coming slide. Raghu, can you show the next slide, please? Okay, so what we see here is the, in a simpler terms, if I say the anatomy of our nodes. So what we have above is a coordinator, which receives a request from the client that's in form of a SQL query. So what we have is a data location APIs first, and metadata interfaces, which meets like a heart for the whole system, keeps the track of where which data source, and within the data source where the files are located. Scheduler further helps us to deploy that particular fragment, the worker which is closest to that data source. So what we have is affinity aware scheduling, which helps us run through whole of the things. Then we have the planner optimizer, which is also quite rich for all kinds of complex query scenarios and all. We have both rule-based as well as cost-based optimization capability built in within that. In one couple of recent enhancements to the optimizers, which we did, were predicates itself. We can push down even down to the data source, so that the traffic within this from data source to our working processing nodes reduces further. We have dynamic filtering. I think we'll cover a couple of them going further in a few slides. We have an indexing mechanism here, which is quite unique. It does not add any cost to the data source and lets us process things further faster. We combine a lot of the smaller files to reduce the work span itself. Combine a lot of small files, merge them together, and process as if they were only one file or smaller in a smaller data chunk or work chunk. I think we'll move on to the next slide. So first thing let's see about the dynamic filtering capability of OpenLooKeng. What we see here is the technique which helps us reduce the cost of joining across two different data sources or within the data sources. What we do using this mechanism is our planner detects where a query has a join, and the join is qualifying for applying a dynamic filtering. So what basic idea here is we have left and right of join. So we call it as a build side and the probe side. So build side fetches almost all the data. Probe side is what gets filtered based on the build side data. So what we do here is we plant one sampler we call as a dynamic filter source. It picks up the data while reading the build table, creates a dynamic filter, supplies that to our dynamic distributed cache. That's again one of the cache we implemented using the Hazelcast framework or the state store mechanism, which we discussed earlier. This cached filters we put to our filtering service, and where the probe node is, like wherever we are scanning the data, there itself we apply the filter early. So thereby applying the join filter lower at the time of scanning itself, reducing the processing needed for the join node to further filter out or prepare the next set of results. That this optimizes the whole the joining of very, very large, like what we're talking about, the big data scale, quite swift and quite fast. I think we can see further. I think this further adds a slight complexity, that is the cross-domain dynamic filtering. What we have, as we discussed, is a cluster itself becoming one of the data sources. So since this clusters, we share quite a few key information, the important information across, being it the metadata, being it some other state across this thing. So while we are pushing down a join node down to a DC node, we can also supply it with the filters which we have got in the source node. So this filter we package like in a Bloom filter this thing, and we serialize that state and send it across the cluster. That further cluster can further send it down to the next cluster, which is under the whole hierarchical structure of the cross DC clusters. I think we'll go to the next slide. Okay, so yeah, indexing is one of the how to say interesting problem when it comes to big data scape. Generally, all our data sources stay at one place, and our compute, our logic, other things are not located at the same place. Our processing is happening in a different node or a different so pulling all the data actually puts a strain onto our network. And since this is decoupled, what OpenLooKeng brings in at OpenLooKeng, what we have brought is a heuristic index layer. Now, this is a framework whereby we expose interfaces which you can also implement to add your own connectors indexing mechanism. We offer some for our data sources like Hive, HDFS, and similar things. So it does not matter what your storage is below, but what we can do is build an index over the data at our end. So this data the index data is not occupying space on the actual data source. So it's not modifying that, but we build that index on our own and use that for our processing. How we do that, I think we'll take a deeper dive in the coming slide. Yeah. So yeah, to the same our anatomy page. What we are seeing here is our heuristic index. Is built in two-layered mechanism. So it's a two-level index. One we have is a sparse index, and one we have is a dense index. So sparse index we use at the coordinator level, where we are churning down the work into smaller fragments and figuring out which all should run what all things. So we apply this index to reduce our search space across that data source into general areas, okay, or files where this data could be, or the part of the file where the data could reside. And based on that, we schedule the same thing and pass to the workers. Workers use the dense index to really look at that specific area within the file. If I say ORC or something, it will be a stripe or something in that order, and really pick out the data. So currently we have different kind of index implementation for these two layers. Sparse index we implement in a Bloom filter or a min-max kind of index mechanism. And the dense index we give out as a bitmap or a B-tree. And it can be extended also. Yeah, that's how our basic indexing thing works, and really accelerates the whole execution while applying the filters to the table. I think we'll go to the next slide. So yes, recently we completed our 1 year of OpenLooKeng. Our first release to open source was last year, June. And since then, we have quarterly made multiple releases. So current running latest release is 1.4.0, and the upcoming release is going to be in December of this year, end of December this year as 1.5.0. So all the key features which Raghu had been highlighting in the beginning pertaining to the business space and looking at the main pain points. I think these releases have gradually been alleviating most of those things, and I think we have a couple of more things to look forward to. Raghu, I believe you would want to highlight some areas here.
Yeah, you can go ahead. Okay, once that was a clean and clips of. We want to talk what we want to do more in OpenLooKeng. So yeah, till now we have talked about it's an MPP engine which fetches the data from the storage, takes it, processes the data, and it can give the output for the analytics. But there are a lot of inefficiencies coming in that. One is the data is fetched everything from the storage to the compute layer, and you have a massively parallel partition of nodes where you want to run this. It will partition means start to process the data throughout most of the data. When the data is done, filter it out and give it up maybe for some aggregations or for something like this. So in this means to say, like I said, too much of data which is being transferred from the storage to the compute, we may have to discard more than 50% of that. And when you're doing the parallel execution, maybe we're not taking care of that, maybe the vectorization or maybe GPU capabilities, or we are not able to use them very, very well. And also the data exchange. When the data, what we are trying to bring, we are not trying to adjust the data based on the network characteristics. Maybe we lose the data most of the times in serialization, deserialization, when you are transferring the data from one node to the copy. The data will have to be copied from memory to the operating system buffers, and the data will have to be fetched. So this brings a lot of inefficiencies for us in our processing. Though we are able to process TBs of data, GBs of data, maybe now we are able to process PBs of data also in a big clusters, but there is a lot of inefficiencies that come into the solution. So what can be done as next in the big data engine? Solution wherein instead of each of the engines, okay, we have listed some of the few popular engines itself, they all have their own local optimizations to process the data much quicker. But still, yes, they have to bring the data from over the network, try to handle that one, convert it into their own form, serialization, deserialization would happen. And this, each one of them bring their MPP or a distributed system, they have to transfer the data across a lot of inefficiencies, like I mentioned earlier. So why not have a common library or a common layer which can handle all this for us? One something like a cache, which has a just-in-time compiler, wherein looking at the plan, it can optimize which kind of operators to use, how to use those operators, and also handle the data in a uniform way, so that based on the engine, the data of the data. So this would help for you to efficiently work on a heterogeneous computing nodes. Meaning to say, as the size of your data center increases, definitely you cannot have the same set of hardware or the same hardware capabilities put into the data center. You may put a different, when you want to upgrade your data center, some of the nodes would get replaced, some would still be the old one, or you build a latest hardware. So when you want to do a cross collaboration between these two data centers, yes, the amount of resources or the capability of resources what we have are going to be completely different. So we are thinking of why not have one kind of a library, which once you write it based on the hardware and based on the engine, it can adapt itself and give you what can. So this is what we are thinking maybe should be the future of the big data ecosystem, wherein you can have this kind of a library, and the engines can take care of distributing the processing, can take care of ensuring at the higher layers there is no data loss or there is no failure of queries. But at the below layers, we can take care of managing the data well, so that there is no too much of data loss or data we have been fetched from the storage, so that whatever we fetch, we can try to consume that. So means to say, push down your predicates or push down your filters or whatever possible till your storage layers, so that the amount of data what we can transfer to the computing layers reduces. Also build a cache so that this data can be reused. The cache can be reused across engines or can be used across queries. And yes, your hyper-converged architecture was the norm, but now with hybrid cloud and with cross-cloud collaborations, having a disaggregated architecture is a common norm. The data has to be brought over the network, cache it onto the computing layer, and then process that. So placing this kind of an library or this kind of a framework at the computing layer and use special purpose built engines. So that would help us to take care of having the same processing capability. Not that the above users need not change their application because a new engine has to be brought. Whatever they are trying to consume with, they can use the same formats, they can use the same interfaces. But yes, plugging in at the southbound will help us to significantly improve the future in the big data engine, which we are trying to work on that. And also to summarize what OpenLooKeng is, its vision is to enable a fast data value realizations. So we want to bring a convergence analysis across cross sources, across cross domains, and try to maintain a one copy of data as much as possible, be as high performant as possible on a SQL on data can be stored at PB levels, TB levels, on a variety of nodes, and there is no data can be fetched. Build features like a heuristic index, which can help to accelerate the data much faster, which can be maybe 2 to 10 times faster compared to the traditional engine. Also support a very high concurrent processing and achieve the end-to-end results in seconds. And also have very good northbound and southbound have standard interfaces through JDBC and ODBC and the SQL 2003 standards, so that many of the BI systems can connect to this relatively easily, and have a very good conversion tools which can help to convert the various languages onto the SQL 2003 format, and also provide an unified data source access framework with rich set of access capabilities which can help to access most of the popular available, and also add many of the enterprise class features like your auto scaling, like a support for AA, and ensure that there is always a service continuity. HA is there, yeah, AA is what is going to ensure that there is no the downtime, and it can help us for that one. Also support the container deployment so that the data can be easily scaled up or scaled down and have a one-click in. Also improving the O&M capabilities and simplifying the integration operations. Also provide features like an IUD, means insert, update, delete, along with ACID transaction capabilities, so that this can help for us to really achieve what is needed as in an enterprise, that there is no data loss, there is no data inconsistency. Yes, the data what we see is always used correctly. Want to talk about, we did many of the things like the heuristic index, pushing down of predicates to the data sources, the DC connectors in 2020. In 21, we are now supporting to go to more than 500 concurrent processing. We are trying to build, this is Omni runtime, which we are trying to do that with analytics performance, a high analytics performance. So working on the part now, and in future we want to build a multi-calculation scheduling, is looking at the function, how do we want to schedule, which is the best place to schedule this computing, and also build the computing for the web or to the cloud. Okay, I think I need to use the word cloud here, wherein we can use the heterogeneous computing capability to realize the fullest hardware capability and ensure that we are able to meet the demands of the current market scenarios. So we did run our tests on benchmark. We did compare with some of our other open source counterparts. Yeah, we can see that on a 10 TB data, we are 28% better, and compared to Impala, also we are very significantly faster, and 32% performance was better than Impala 3.4. And also Impala was able to run only on not all 100% of the TPCDS, only around 78, and OpenLooKeng is able to support 100% of TPCDS queries. So to that, I bring a closure to our presentation, and thanks a lot for your time. Yeah, we can take questions. And our OpenLooKeng community is very vibrant community, and feedback. We request all of you to contribute in whatever way form, means possible. Let it be the feature or a feature request or a contribution to documentation or bugs, and always be active on our mailing list and help us in promoting our community. And also OpenLooKeng, and we have put this as a last. There are many ISVs who are already adopted OpenLooKeng to give entities in China are able to use our solutions. In finance, in ICT domain, they are able to use. The internet companies, the web companies are using, and many other companies which don't fall into this categories have already adopted OpenLooKeng to realize their analytics capabilities. Yeah, means can always visit our website powered by HTML and look at that. What kind of capabilities are people are able to. Yeah, I want to say thank you for your time, and I think we can take questions. Okay, it looks like I think there are no questions for the moment. So shall we bring a closure to the presentation?
Yes, sir. Thanks for your time and efforts, and it's a pleasure having you with us here.
Thank you. And thanks for opportunity to speak about our project here at OSI.
Yeah, thanks very much. Thank you.